Morning, guys. Right, your homework from Tuesday was just to write up the last experiment, um, the one about the catalyst. So, chapter 12 is finished. We have yeah. Okay, so we have the exo and endothermic reactions experiment to do, and then we have the 4 rates of reaction experiments to do when we get back. But other than that, other than them not being finished, we're going to move on to the next chapter, which is chapter 14. I don't know, however you view it, fortunately or unfortunately, there's more experiments in this chapter. Not too a lot of them are demonstrations, to be honest, so I'll do them and you guys will just watch them, so at least that'll be a bit quicker. Yeah, I'm just a little bit anxious about how many experiments we're kind of leaving over because we still have to do our CBAs when we go back. So yeah, we'll be busy, but at least it'll be a lot of practical. So you'll get to get in and just do the experiments. I suppose the only thing that it will require from yourselves is to be quite organised, because normally, I teach you something for a class and then we do an experiment. I teach you something and we do an experiment. Here, I'm teaching you now, and we're going to do the experiments in like 5 weeks. So it's going to, I suppose, require you to do a bit of reading, pre-reading before the experiment, but we'll figure it out. Okay. All right, so moving on to chapter 14, which is just called chemical reactions. We're going to talk about bonding, different types of chemical reactions here. We've obviously been doing quite a bit of chatting about chemical reactions when we were doing rates of reactions. So some of this will be familiar to you, and we're going to talk here specifically about reactions with metals, which are really nice reactions, reactions with oxygen, just different types of chemical reactions, and moving into bonding then. All right. Okay. So I think we talked about this before. How can you spot a chemical reaction? So there's a load of different ways depending on the reaction. So you might notice a color change. It was, you guys, wasn't it, the concentration experiment that we're doing with rates of reactions? Remember I told you that when we mix them, we're going to put the X down on the page because the reaction produces sulfur and it's going to turn like a yellowy orange colour. So that would be an example of a colour change, which hopefully we'll see. It might give off a gas. I'm going to think, did we do any of those reactions? I don't know if we've done any of those. Get hot, get cold. We're definitely going to do them because a reaction that gets hot is called an, fill in the blank, exothermic reaction, and then a reaction that gets cold is called an endothermic reaction. A reaction that gives out light, and the reaction with metals give out light, so you'll be able to see that as well. A one that makes a smell, that sulfur one, the colour change one, also stinks. One that forms solids, I don't know if we're going to do any of those. We do crystallization, but it's not part of this, I don't think. So, but we will do it. So that's when they react. You have your reactants, and when we reach the activation energy and the reaction takes place, they actually start to like clump together, and you create solids, and they look like little crystals. So that's just different changes that are sort of evidence that a chemical reaction has taken place. Another good point about a chemical reaction, we did talk about physical changes versus chemical changes. And so chemical reactions, when they take place, the kind of big defining factor on them is that they're really difficult to reverse. Most of the time, close to impossible to reverse. Sorry, I'm just trying to find this on the iPad. Oh, I'm in maths. So chemical reaction are usually difficult to reverse, and that's kind of a defining factor in whether or not a chemical reaction has taken place. So a chemical reaction is not the same as a change of state. A change of state, like from solid to liquid or liquid to gas, is called a physical change. And physical changes can be reversed. So if you have ice and you melt it, you can then take that water, put it back into the ice tray and freeze it again. And you're going from state to state. It's fine. We did a good bit of this, but obviously if you boil something, it is difficult if you just let it boil off to get it to turn back into water. But if you use, I don't know if you remember this, but if you use your distillation apparatus, you can, when it boils off, do you remember it goes through the condenser and it turns back into liquid? So it is possible to go from your boiling water back into liquid. However, you look here, when an egg is fried, the proteins change to a different form and that cannot be reversed. So you can't unfry an egg. Okay, there are some reactions where the products can reform reactants. They're called reversible reactions. We don't deal with a lot of them at junior cert. If you do leave it to chemistry, you deal with reversible reactions. So some reactions are reversible, but most are not. Okay, so different types. Some of these are more important than others, to be honest. I kind of got the list from, this lower list is from your book. This is from the Doodle website. So oxidation, reduction, thermal composition, displacement, neutralization, combustion. We have oxidation again, neutralization again, electrolysis, and decomposition, which is up here as well, just thermal decomposition. So yeah, there's quite a few different types of reactions. Some of them are important and we're going to spend a bit of time on, and some of them you're not going to deal with too much at junior cert or junior cycle. So the first one here is oxidation. This is an important reaction. An oxidation reaction occurs when a substance reacts with oxygen. Okay, so you can hear it. Oxidation, when a substance reacts with oxygen. Okay, so when a substance is oxidized or undergoes oxidation, then it gains oxygen atoms, so it gets extra oxygen atoms, and rusting is an example of an oxidation reaction. So when something is left outside, so it has access to oxygen, and then it also needs water, so normally rain or something like that, and you end up with rust. So the chemical reaction is here. It's iron that rusts, so you need iron. You need water, which for most things that are left outside, it's normally in the form of rain. And then you need oxygen. Okay, so because oxygen is involved, it's an oxidation reaction. And you end up with iron oxide, and iron oxide is the chemical name for rust. A reduction reaction is the opposite. So it undergoes reduction when it loses oxygen atoms. Okay, so over here you have your magnesium and your oxygen, and they're holding hands, so they're bonded together. These are the reactants. Once the activation energy is reached and the reaction takes place, then what happens is the magnesium here has lost this guy, lost the oxygen. So it's a reduction reaction. Like these ones, no, I'm not sure how important these are going to be. Thermal decomposition. I think it's probably more important just to understand the words. You'd be able to take it apart. So thermal implies heat, and decomposition is when you're breaking up a substance into smaller pieces. So yeah, they have an example here of calcium carbonate, and if you heat it, so the Bunsen is down here providing the heat or the thermal part, it breaks up into copper oxide and carbon dioxide. So that is a decomposition, so I wouldn't worry too much about that one. No, don't worry about displacement either. Now neutralization, this is important. Neutralization would be the reaction between an acid and a base to neutralize it, and we do study acids and bases. So when you react an acid with an alkali. An alkali is another word for a base. So you react an acid with an alkali, you get a neutral substance. I always think of this in terms of like maths. So your acid would be like your -2, and then react that with a +2 and a -2 and a +2, create 0. For those of you who are particularly mathsy minded. And that's essentially what's happening, okay? If you mix an equal strength acid with an equal strength base, when they react together, you get a neutral substance. So it is neither acidic or basic, it is neutral. Okay, we're going to talk about that in way more detail when we study it. So yeah, they have an example of reaction there, and we actually do that. That's one of our experiments that we're going to do in the acids and bases chapter. I can't remember if we're doing acids and bases before the end of the year, but that's one of the experiments. We react hydrochloric acid with sodium hydroxide and we produce sodium chloride, and sodium chloride is neutral. And then you can test for that neutrality. So we have this substance that we drop in, and in an acid it turns red, in a base it turns blue, and when it's neutral it stays like a yellowy colour. So you can test then if what you've produced is neutral, which it should be. So would I call this another type of reaction? Probably not. A combustion reaction. So, it does say it. Okay. A combustion reaction is a reaction. So they're particularly talking about the car engine here. So they're saying that petrol burns with oxygen. But if you have a reaction of a substance with oxygen, then what is that reaction called? Give you loads of time to say it there. Yeah, it's an oxidation reaction. Okay, so a combustion reaction is just an oxidation reaction, really, which I do think they attempt to address down the bottom. So yeah, when petrol and oxygen are mixed together, you produce carbon dioxide and water. So this is why we're moving towards, sorry, I can't write and talk at the same time. This is why we're moving towards electric cars, because the production of carbon dioxide in a petrol burning combustion engine is environmentally hazardous. It's producing carbon dioxide, which is a greenhouse gas, so on and so forth. But anyway, when petrol reacts with oxygen, it produces carbon dioxide and water, and also produces heat, and that's the energy used to drive the car. Okay, it says combustion involves reacting with oxygen, so it can also be classified as another type of reaction. Which one? I've already addressed that. Yeah? Yeah, I just want to briefly talk about combustion reactions a bit more. But anyway, I just want to show you this. In a chemical reaction, the total mass of all the reactants always equals the total mass of the products. It is known as the law of conservation of mass. Okay, that's really important. The total mass of the reactants is equal to the total mass of the products. So there's if I can show this to you, where did I say it was? Chemical reactions part 2. Just bear with me a second. This one. Okay, so this is a reaction between lead nitrate and potassium iodide. Okay, so the mass of the lead nitrate and the potassium iodide is measured. Okay, so the lead nitrate is in one of these boiling tubes and the potassium iodide is in the other one. They weigh it and they're getting 32.1 grams, including the glassware. Yeah? Okay, so next they're going to remove the rubber bungs from the top of the boiling tubes and they're going to mix the two reactants together. So when the two liquids mix, you get a yellow solid being formed. So that is evidence that a chemical reaction is taking place, because first of all we have a colour change, and second of all we have a solid being formed. And then what they're going to do is reweigh it. Okay, so just watch that happening. So remove the bungs, mix one into the other, you have your yellow solid. They put the two back, because remember we weighed the glassware the first time, so we're going to now weigh the empty boiling tube on the left and then the boiling tube on the right in which the reaction is taking place. And when they do that, you get 30, oh sorry, I didn't mean to do that. You get 32.1 grams again. Okay, so it's something we can check. We're going to do, like I said, loads of chemical reactions, and you can check it on any of them if you wish, but it's called the law of conservation of mass, and it's quite important. Okay, why doesn't the mass change? It's just a nice little picture. So you're not changing the amount of atoms that are in the reaction. All you're doing is bonding them differently. So here we have the sorry now, where am I? Here. So these guys here are the reactants, and then these guys here are the products, okay? And if you try, I mean, you can tell even by the color code. So we have this fella in the reactants, and he's also there in the products. There's not more of him, it's just him. And this one here is there and also in the products. Likewise, the red one is there in the reactants and the products, and so is the green one. Yeah. The only difference is they're bonded differently. So in the reactants, A was bonded with B, but in the products, A is now bonded with C. Okay, so that's why the mass remains the same, because you're not really messing with the amount of atoms, you're just changing the way they're bonded. Okay. So I just want to briefly talk about combustion reactions. We just did there a second ago anyway. So chemical reactions happen at different rates. We know that. We also know you can mess with the rates. And how do we mess with the rates? There are 4 ways. We can change the temperature. We can change the concentration. We can change the surface area. Or we can use a catalyst. Okay, so reactions naturally take place at different rates anyway, and then you can artificially mess with that as well. And so, like we said above, combustion is an oxidation reaction, and it's a fast one. It's a really fast oxidation reaction. And when a substance burns, it mixes with oxygen in the air and gives out energy in the form of heat and light. And that means it has to be an exothermic reaction, because it gives out energy. Okay, so that's important, that a combustion reaction is exothermic, which I actually think it was the example, the everyday example I gave you for an exothermic. Okay, so it's all linking together. The fuel is a substance that burns in oxygen to produce heat. So different types of fuel. So a couple here: turf, coal, natural gas, candle wax. And they are all fuels which will burn in oxygen and produce heat. Just an important word, I suppose. All of these, turf, coal, natural gas, and candle wax, they're made up of hydrogen and carbon, so they're called hydrocarbons. Okay, I know we also call them, like turf, oil, natural gas, we call them fossil fuels, but fossil fuels are hydrocarbons. Okay, they're made up of hydrogen and carbon. So this is a nice little experiment. I'm just going to show you here. It's on this thing as well. Number 3, I think. Here we go. Right. Okay, so what happens when the bell jar is placed over the candle? So I don't know if anybody has ever had, they're called like snuffers. They're little, they're actually about the shape of a bell jar, but they're small. and they have a little handle on them, and they're used to put out candles. So when this bell jar goes down over this candle, the candle will go out. Do we know why the candle will go out? What is it that by putting the bell jar down over the candle, what are we removing? There it is, going out. So not instantly, but it went out. So why did it go out? So this is a burning flame, which means it's a combustion reaction. A combustion reaction a combustion reaction is an oxidation reaction, a fast one, and an oxidation reaction uses oxygen. So it's using up oxygen. So when you put that bell jar down over it, there's a certain amount of oxygen trapped in the bell jar, which is why the candle doesn't go out instantly. But once all that oxygen is used up, then the flame goes out, and that's what you're seeing. Okay, here's another, it's the same experiment, okay, but this time the bell jar is placed over the candle and the candle is floating on some water. Okay, so watch what happens. Let's see if we can see that again. Hang on. Okay, so here it is now, it's in the water, and you get that little rise. So what's happening there is actually the exact same thing. So when we put the bell jar right down over the candle continues to burn because it's using up the oxygen that's trapped in the bell jar. But as it uses up that oxygen, there's more space because the oxygen gas is taking up a certain amount of space. But then when the flame uses it, it's not there anymore. So that space is then occupied by the liquid, and it sort of gets drawn up to fill in the space that's been evacuated by the oxygen gas. So it's a nice little experiment to show basically that combustion, so a burning flame, uses oxygen. And the fire triangle, I'd say you've come across this before. Very, very important. 3 things needed for combustion to take place, and they are heat, fuel, and oxygen. If any of these elements run out, the fire will go out. Okay, heat, fuel, and oxygen. And then just this one, I just thought this was interesting. An incomplete combustion reaction. So if there is not enough air or oxygen for a complete combustion reaction, then the reaction is not completely finished. The word equation for an incomplete combustion reaction is as follows. So if you have a fuel, like your turf or your natural gas or your candle, whatever it is, and you mix it with oxygen, okay, but there isn't enough oxygen, that's how carbon monoxide is produced. Okay, and I'm sure you've heard of carbon monoxide. Instead of producing, so in our other combustion reaction, like in the engine, we were producing carbon dioxide. Carbon monoxide, now while carbon dioxide is a dangerous gas for the environment and is a greenhouse gas and it does cause harm, it's not dangerous the same way carbon monoxide is. So carbon monoxide is colourless, odourless, toxic gas. There's ads on the telly for this. You're supposed to have a carbon monoxide alarm. Every house is supposed to have a carbon monoxide alarm in case for any reason your gas boiler basically starts working incorrectly or is deprived of oxygen, and it attempts to burn in the absence of oxygen, and it produces carbon monoxide in this incomplete reaction. It doesn't smell like gas. You know, if methane gas was leaking, you smell it. There's no smell of carbon monoxide. And there's been too many absolutely tragic accidents where a boiler was working incorrectly, produced carbon monoxide, and it kills in minutes. And there doesn't need to be a lot of it. So they have here, your boiler should be serviced regularly. Rooms should be well ventilated. So now when you build houses, every room has to have like a vent in it, and so that if some carbon monoxide did leak into a room, that hopefully it would just be sucked straight out of the room again through the vent. and carbon monoxide detectors, again, to meet current building regulations. You need a couple of carbon monoxide detectors in the vicinity of your gas boiler. Yeah, they need to be certain distances away. So like I have one here in my kitchen and my gas boiler's out under my stairs, and I also have one up on my landing, and that's where we were told we had to have them. Okay, so that's it. No homework, just take down your notes. Okay, and we'll keep going with that on Tuesday. All right, thanks guys.